a joint work with Mitchell Jones. Is an ex-student of mine. He graduated just a month ago, so officially he's Dr. Mitchell Jones. And this paper involved questions about nets. So what is an epsilon net? I give you a set of points in the dimensions. I give you a set of ranges, say the set of all balls. And a net is a subset of the points such that for every range that contains an epsilon fraction of the points, the net, which is a subset of the original point set, contains a point inside the net. Inside the range, right? So the way to think about it is that the net stubs all the heavy ranges. And heavy here means that you're containing epsilon fraction of the points. So the existence of epsilon nets was proven by Hauser and Weldon in their celebrated paper from '87. They showed that a random sample of appropriate size worked. The random sample is roughly of size 1 over epsilon log 1 over epsilon. There is a delta, which is this VC dimensions, which I'm not going to go into formal definition of what it is. But to all natural set of ranges, it's a constant. And with the hindsight of time, we now know that the Hauser and Weldon result, in fact, is an easy consequence of the original work of Wapnick and Chernovenkis. Essentially, you can prove it in one paragraph. The only reason I mention it is because the work by VC usually cited a paper from '71, but it turns out that they published it, in fact, in '68, if you care about such things. Okay, so let's see a natural example where we don't have any epsilon net. So consider the set of ranges now are all convex subsets in the plane, and then we take endpoints and put them, let's say, on the circle. And for every subset that you pick to be your net, the trick is going to pick all the complement points, right? And take the convex hull. The convex hull is going to avoid the net, and as such, the net would fail to stub it, right? Now, of course, in this case, this is... and the reason why this is happening is because the VC dimension, this delta dimension earlier, is infinite in this case. And somehow it's natural, right? Because these polygons that are under consideration in this case have unbounded number of vertices, right? We need an unbounded description of the entity. But in this case, this is not very interesting because you can just put points of the net, instead of being a subset of the points, you can just put some point inside the circle and they would easily stub any heavy range. So this gave this rise to this concept of weak epsilon nets. So we have a set of points, but now I'm allowing you, and we are looking now, a set of ranges, all convex bodies in the dimensions. And now we are looking for a small set of points that stubs all convex ranges, convex bodies, containing at least epsilon fraction of the points. And it's not a priori clear why they exist. And proving their existence, in fact, is a non-trivial exercise. There was a long sequence of papers on this problem. Recently, Nathan Rubin improved the upper bound, so we know that it's slightly better than 1 over epsilon to the d. The interesting thing about his upper bound is that his proof for upper bound in 3 dimensions and higher, and its proof for 2 dimensions are different, which is kind of curious. On the other hand, the lower bounds we have is very weak. It's essentially 1 over epsilon some polylog. So there is a huge gap, and in fact, closing this gap is one of the major open problems in discrete geometry. So this work started by saying, okay, all those weak epsilon questions are too hard. Let's look on something much easier. Let's cheat. And the natural way to cheat is to use a Kflat, right? So a Kflat is a k-dimensional affine subspace. In particular, one flat is just a line. So now I would like to pick a subset of Kflats that stubs all the convex bodies that are heavy. And weak epsilon nets, the regular weak epsilon net corresponds to 0 epsilon nets, essentially. And the intuition is that as you increase K, you're making your knife bigger and bigger, and it should be easier to stub the convex body, so you expect the net to be smaller. And in particular, an immediate construction follows by taking the point set in the dimension, projecting it K dimension lower, using the weak epsilon net construction in the projection, and then lifting it back. The reason being is that every net point, weak net points, lifts into a K-flat, but can we do anything better? So again, that seems quite hard, so we decided to look on a much simpler problem. We are looking on the unit hypercube, and now we care only about the volume of a convex body. So we are looking on convex body that takes at least epsilon fraction of the cube. And now the rule of the game is that if a convex body takes more than epsilon volume, then there is one flat in our collection at least that stubs it. So here's our results. We showed that one can get a K epsilon net of size of what's written on the slides. The important thing about this bound is that we have an upper bound and lower bound that are matching for K larger than 0. The important thing about those lower and upper bounds is that they are smaller than 1 over epsilon. So we are getting sublinear bound, which is interesting. And if we insist on using 0 nets, right, essentially points, namely we're back to epsilon nets, then of course you can get you can get the bound, the standard bound for an epsilon net, but epsilon net bound is not explicit. It's a random sample essentially. There are deterministic construction, but again, the algorithms don't give us an explicit construction in this case, and they're complicated. So we give an explicit construction. The bound is by polylog factor worse than the standard epsilon net bound, but the construction is simple and explicit and hopefully nice. Okay, so one comment about 0 epsilon nets. So we care about 0 epsilon net for the unit cube, and the key observation is that it's just a net, a regular epsilon net, and the reason is because every convex body can be approximated up to a scaling by factor of d by an ellipsoid. This is a John ellipsoid theorem. So if a convex body is large, it's contained in a large ellipsoid, and this ellipsoid, you just need the net for that. So really, if we are working only on a volume measure, we can concentrate on ellipsoids. So our problem is in fact even easier. We just really need to think intuitively about ellipsoids. Okay, the lower bound is pretty easy. So we have a collection of K nets, and we want to stub all the heavy bodies that have volume at least epsilon in the hypercube. In particular, you need to stub the ball of volume epsilon. So the key observation is that such a ball, if we just care about stubbing those balls, every K-flat defines a cylinder-like area which it's cover all the center of the ball that are located there, if we're using balls that are exactly of volume epsilon. And we need a set of cylinders that cover the unit cube, so you can compute the volume of each one of those cylinders, and that gives you immediately a lower bound on how many cylinders or K-flats you need to cover the hypercube, which gives us the desired lower bound. Okay, let's discuss maybe the easiest case, which is 1 epsilon net in 2 dimensions. So we have the unit square, and we want to start with lines, and of course you do the obvious thing. You just put a grid, which side let's square root epsilon. You have 1 over square root epsilon lines, and every grid cell is area epsilon, and we are done, right? So that's not very interesting. But let's now try to do it for points, right? We want to now build a Epsilon Net for points in 2 dimensions. And the idea is that we're going to take the line in the middle of the cube, of the square, and put a very dense set of points on it. And now the idea is that the body that contains a lot of area cannot just have a lot of volume on both sides because and get in between the points like in the drawing, because we are dealing with convex shape, and since we are dealing with convex shapes, really if the spacing is epsilon between those points, either the convex shape has to be extremely narrow to have a lot of volume on both sides, but then it has small area, or it has to be committed to one of the sides, but then all it can do is peek into the inside. Right. Now what we do, we of course apply the same construction to the y-axis. This looks like a quadri, and that's exactly what we're going to do. We're going to continue in this fashion, where in the lower level we can use less dense points. Right. And as you can see, as we go down, we can still have creeps that peep through these screens, but the area they peep through are really small. Right. That's intuition. And we do it until we get to the bottom, right? And the important thing about this point set, it's very confusing, but the important thing is that in the bottommost level, we just have a uniform grid, essentially. Okay, so, and now you go to the calculation. Every level have 1 over epsilon point. We have log 1 over epsilon levels, because once we get to the level where every grid cell is area epsilon, we can stop. And as such, the size of this is 1 over epsilon log 1 over epsilon. So that's good. We need to prove, of course, that this works. So the proof of correctness is somewhat interesting. So think about your convex body in the plane, and think about, for every coordinate in x, think about cutting it with a line, and a vertical line, and the length of the area of the intersection. And think about the function that the function of this slice length. So this function is the screen hill on the left. And by Brun-Minkowski inequality, we know that this function is convex. And that's very useful. Why is it useful? So look at the point where this hill function gets the maximum, right? And the basic idea is that this hill function, if you look on the roughest grid we have, which is hiding in the point set, which is this roughly square root epsilon with square epsilon grid, then if you look at this hill function, it cannot contain this square, because if it contains this square, you lift it back to the original shape, you get some kind of a parallelogram, and now it's easy to argue that it must contain one of the grid points in this rough grid, because this rough grid must intersect this trapezoid somewhere along the x-axis, and the length is long enough that it must stop one of the points. So if the square is containing the hill function, we are done. So the hill function must avoid this square. And intuitively, what really our construction is doing is that instead of having one square, we have this collection of logarithmic number of rectangles, which are doubling in width and halving in height, all concentrated in this bottom left point. And the hill function, if it contains any of the vertices of those squares, then we are done. It must be stubbed by the construction. So it must be that the hill function avoids those vertices. Effectively, it's avoiding the hyperbola defined by those vertices. And this hyperbola, it's easy now to argue that every convex function can evaluate most, let's say, epsilon over 8 under the hyperbola, because every triangle that is tangent to this hyperbola evaluates most epsilon over 8. So that's intuitively the proof. And that shows the correctness. Okay, let's go back to the case of lines. We want to do lines in space, which is kind of maybe the most interesting case that enlightened the idea. So the basic construction, again, we're going to use those two-dimensional screens, now made out of lines, to stab the objects. And we're going to have very dense screens and then sparser and sparser screens, where the densest screen, again, is going to have a length quote epsilon. And now we're going to do the same construction. We are starting with the unit cube. Think about it as an octree, a quadtree if you want. We look on the halving plane. We put on them in the top level the densest grids. Then what we do, we continue this function recursively. The number of levels is, you have to pick it very carefully. But the important thing is that as you go one level down, the screen you're using gets rougher and rougher. So you have more screens, but the resolution gets rougher, so things kind of balance out. And you do the calculation, which I'm not going to do now, and you get this bound that I promised you, right? So you in 3 dimensions, you get 1 over epsilon to the 2/3. So summary of our results. We showed K epsilon net for the unit hypercube of size as written on the slides. We got an explicit epsilon net for the unit cube of size 1 over epsilon log to the d minus 1 over epsilon. And the nice thing about those constructions is that they're all deterministic, explicit, and pretty simple, which is nice. And there are a lot of natural open problems for further research. For example, what about using lines for a point set? So it's easy to show that already in the plane, if you just have 1 over epsilon clusters, then a line can stub only 2 of the clusters. So you need really 1 over epsilon lines. So in the plane, it's not very interesting, but in 3 dimension already, I don't know anything interesting better than essentially 1 over epsilon to the true half. So it would already be interesting to do something there. Okay, so conclusion, we showed sublinear result on size of epsilon nets, K epsilon nets for volume measure of the hypercube. And the major open problem is, can we do something interesting now for the standard setting? This is it. Thank you for listening to me.